Hello, welcome to what would have been the second meeting of CRIM 7920, Survival Analysis and Longitudinal Data. So in this meeting, we will be discussing regression with panel data part 1. So splitting this out into, let's say that we have panel data. We wish to perform a regression analysis with those data to see how some features of our outcome variable y vary with our different predictor variables. How can we go about that regression analysis while accounting for some aspects of the benefits and complications that panel data bring? So in this particular class, what we'll cover is just an overview of the model notation that we'll be using and just a brief hit on maximum likelihood estimation. Then we're going to start thinking about when we conduct a regression analysis, how can we begin some mode of handling our dependent observations. So the two that I'll cover in this class are robust standard errors and generalized least squares. So we can still think about these in the way of, I'm conducting a regression analysis. In one sense, I just want to keep going about my business, and regardless of what that dependence looks like, that some observations are correlated with others because they're coming from the same units. I would just like to, correct the violation of assumptions, by kind of penalizing myself. That's robust standard errors. Or what we could do is think about what the nature of that dependence looks like, and maybe we can model that and incorporate that into our estimates. And that's what we would do with generalized least squares. Then, as something that would be useful going forward, and kind of how we'll handle a lot of decision making in this class, we'll cover multi-model inference. How do we choose the best fitting model among different alternatives? So recall, just as the overview, with our panel model, we have several variables and we have several parameters that we're interested in estimating. So our dependent variable, or the outcome or the response, will be y sub it. It has sub it because it varies between units, and t, it varies within units over time. So anything with just an I subscript can only vary between units. Anything with an IT subscript can vary between time points or within units who are observed over multiple time points. So we'll always have an x for our independent variables that vary over time. W sub I for our time stable predictor variables. And so these would be things, measures of our units that do not vary over time. And by that, I also mean that conceptually and theoretically, they do not vary over time. It is possible to have, a x sub it measure that just has very little variance. So it de facto does not vary over time. That's always very sad when that happens. We don't want that to happen because we want variation. So those are our variables: outcomes, time varying predictors, non-time varying predictors. Parameters that we want to estimate, we have alpha, for our intercept. And so again, this is our starting point. This is the mean of y when all x are equal to 0. Now this is not super important in the context of just regression with panel data, but as we get into growth curve modeling, it will become very important in terms of how we want to think about the intercepts there. Also a little bit with multi-level models and the hybrid approach, which we'll cover next week. We have our beta parameters. So these are the parameters that describe the effects or the associations of time varying predictors on the outcome. So given, when we compare two units, who differ on, xit by 1, or the same units who vary on xit by 1, this is the predicted shift in the mean of y. And so we'll cover some of that. And then we have our gamma parameters, which describe the slope of a time stable regressor. So this is something that does not vary over time. These do not have to be categorical. These can be numeric measures that do not vary over time. And then also we have our random error term. So this is we put the linear predictor here of this plus this all together. We will get a predicted value for the outcome. Those predictions are sometimes right on the money. Sometimes they're way off. EIT quantifies how far off our prediction is from the actual value that's observed for Y. So we're going to start building on this model a bit to begin accounting for panel data structures. And you'll see kind of how that works. Okay. So the first thing that we can do, so like kind of at the very base is, recall that we have as our motivating example, we have this data set of youths, of young people from the National Longitudinal Survey of Youth. We have 5 waves of observations. So they were interviewed every 2 years from 1998 up to 1996. I think that math checks out. And so we have variables like our outcome is that behavioral problem index. So it's a numeric measure of internalizing and externalizing behaviors. Higher values indicate more problematic behaviors. And we have time varying predictors like our home environment, so a caring home environment versus a non-caring, and again, that's a numeric score, and whether or not the family is in poverty status. That can vary from time point to time point. Okay. So one of the main things that we would need to account for the effect of time in a variable like this, at the very base, is that we could include a variable that captures the fact that we are observing different observations at different time points. And so in this instance, this first instance, what we'll do is we'll actually create a time as a categorical variable. So even though time might have values of 1, 2, 3, 4, 5, for each interview that the youth does, let's make that a categorical variable. And what this would do is it would essentially estimate separate means for the outcome at each value of those different time points. So we'll call this mu sub t. All right, so basically, the mean, of Y, but notice it's just sub t. So it has a unique value for each estimated time point. What's really interesting about this is when you think about what an intercept does, recall that it communicates, what's the mean of Y when all other X are equal to 0. What this essentially does is if we're estimating more or less a separate intercept for each time point, it's kind of like saying, when all X are equal to 0, but time is varying, right? What is the changing nature of the outcome over time that essentially affects everybody equally? And so we could think about this in a couple different ways. Like, for instance, let's say that there's some effect that, let's say like a kind of like a history effect or a period effect that is impacting all units equally, but changes over time. So let's say that in the middle of our study, some lunatic is elected to the White House, for instance, and that causes just a shift in behavioral problems across all units, but it affects all of them equally. That information is now captured, and that's now removed, from these other parameter estimates that we're interested in. Because if we're going to be talking about, what's the change in the outcome, YIT, given, a unit shift in X or different categories of W, for instance, we don't want those to necessarily include just these overall shifts in time that are occurring over the outcome. So our basically dummying out of time here, different means for time, will essentially allow us to capture that information. So in R, this can be accomplished just by including time as a categorical variable. In this instance, time is actually numeric, but in the model formula, I have specified it as a factor. You could always specify as a factor, beforehand. In Stata, I can't remember exactly what you do with this. I think, isn't it I dot time, I think is what you would do, but it's basically specifying that variable as like, hey, software, this is a categorical variable, even though its values are actually numeric. But so what this will do is we have 5 time points. So this will actually create t-1 coefficients in our model that reflect the mean of y at each time point when all other x are equal to 0. So here's our model over here. This is the exact same model that I had presented in the previous class. And so, what we have is you can see our intercept, and we have our factor time 2, 3, 4, 5. So what this is doing is this is indexing just essentially mean shifts in the outcome over time. And so what we see from these estimates, it was pointed out that this is our mean behavioral problem index at time 0, or at least because it's factored out, it's the first time point. Yeah, if this was numeric, that would be a problem, but it's categorical. So whatever the first time point is, time 1, that is the mean behavioral problem index when all other x are also equal to 0. And again, for some of these, that might not necessarily make sense. So like, your mother was 0 years old when this child was born. Maybe we want to do some centering on this at some point. Let's ignore that for right now. So what we can see is this is an estimate of how different the behavioral problem index is going from time 1 to time 2, from time 1 to time 3, from time 1 to time 4. And notice that none of these are compatible with the data are not compatible with the parameter being equal to 0. These are failed to reject. This one is in terms of time 1 to 5. And so you can see that that difference actually does look like it could be different. So this is kind of the baseline shifting over time in the behavioral problem index. By factoring this out and making time a categorical variable, essentially what we've done is we've taken this patterning and we have just removed it from all of these other parameter estimates. So now this is like saying, after accounting for just the trend in behavioral problem index over time, we can now estimate shifts in home environment, impacting behavioral problem index, shifts in poverty, comparison of males to females, et cetera. We can do that taking out those time effects. Now, this is a very, and just showing you explicitly how these things are connected to one another. Like these are what these parameters are doing. If we actually added these up, the intercept, so mu1 plus mu2 would give you the mu at the intercept at time 2, right here. So this is a very basic treatment of this problem because there's a couple things that are still going on here. Even though we have taken basically the form of time out of the equation, and when I say the form of time, what's nice about this is really any form of time. So because we estimate separate values for each separate parameters for each time point, then if the trend over time, goes up and then down and then up again and then down again, or is flat, or is a V in this way, any one of those possibilities would be covered, by estimating separate parameters for each time point. Now that's not very efficient. Like if you had a lot of time points in your data, so let's say like 10 plus, you are now estimating, 9 parameters, to capture time. In this case, like in this particular case, do we really need 4, unique parameters to capture the effective time here? Like probably not, but that's something that we'll cover when we get to growth curve modeling. So in any case, we're taking basically the functional form of time out. Okay, good. But when we look at these parameters, these contain a lot of information. This effect for poverty, for instance, contains within unit variation. When we compare one unit at a time point when they were not in poverty to that same unit when they were at a time point and they were in poverty, this is the expected shift, in the outcome. The behavioral problem index will go up. At the same time, when you compare one unit who is, in poverty to another unit who was not in poverty, this is that change as well. the assumption is that those two effects would be the same, all right? This is something we'll get more into with random effects and multi-level models, but what I'm saying is that these parameters contain both within unit variation and between unit variation. We don't know what mix of those two things is producing these parameters as we see them here. Eventually, we will want to find that out. But if this model is to be correct, for right now, we need to assume that those two effects, the within unit effect of this shift in this and the between unit effect, can be captured by these parameters. And again, this is very important for our time varying variables, which are home and poverty. Additionally, down here, you'll see our residual standard error. So this is on average, how far off on the behavioral problem index our predicted values are from the actual values on average. Thought a sneeze was coming. You might recall from just your general linear modeling coursework that what we assume is that this rate of error will apply to the entire distribution of y. So as we go from the lowest behavioral problem index to the highest behavioral problem index, this is how far we are off in our predictions on average. That's the homoscedasticity assumption. If that is not correct, then we have heteroscedasticity. And that means, this would be a good time for me to ask you all, hey, what does that mean for this? And so maybe you'll pause the video and think about that for a second. That means that our standard errors are likely to be underestimated because we are assuming, hold on, I am not going to reboot my computer. Come back in 4 hours. Because we're assuming that this residual variance holds, over the entire distribution of y. Okay, so let's talk a little bit more about this then. So that's our basic premise, that we could just dummy out time and remove it from our parameters. But before we can get into, okay, what's a more principled approach with dealing with dependence and handling that within unit and between unit variation on our time varying predictors, let's talk briefly about maximum likelihood estimation. And because that will be essentially the baseline that we're moving forward with. So some of you, depending on your background, this would be like, for me, before I would come into a class like this, when I learned regression analysis, it was almost all based on OLS regression, ordinary least squares. And it wasn't until I was later in my doctoral program I even heard of what maximum likelihood estimation is. But what we're doing with maximum likelihood is we are attempting, how do we derive the parameters that can describe, the effects of the associations. I'm trying not to use causal language. The associations of our regressors, our predictors on the outcomes. So what maximum likelihood estimates ask is, so given the model that we have, so yit given alpha or mu sub t plus beta xit, et cetera, given the model, what are the parameters that would maximize the probability of observing the data as they are? And so there are a few ways that we can arrive numerically at parameters that will do that. So, essentially, maximum likelihood requires some optimization criterion. So what are we essentially trying to accomplish? How do we know when we've maximized the probability of the data? Well, in OLS regression, what we're trying to do is minimize that sum of squared residuals. So take that residual variance, that amount that we're off from all of our predictors, and what's the set of parameters that minimize that value? That if you change that value even slightly, the parameter values, it would increase the error. Once we get to that point, we know that we've minimized sum of squared residuals. Maximum likelihood does not explicitly think in that way. What we're essentially trying to do is minimize kind of a generalized deviance function, which is conceptually quite similar to minimizing sum of squared residuals, but it can be different depending on, hold on. Oh my God. Ooh, excuse me. There we go. It can be different depending on the likelihood function that we use. But as we'll see, OLS is actually a form of maximum likelihood, just so that we're clear that we're talking about the same thing. So just to highlight, like on the model on the left is I have that previous model as it was estimated with OLS. Model on the right is estimated with maximum likelihood estimation, or a Gaussian likelihood function with an identity link. I.e., these two things are equivalent. So OLS is a specific form, of the MLE. I just want to be clear that when I'm talking about maximum likelihood, and I mentioned we're using a Gaussian likelihood, we're using an identity link function, that this is OLS regression, that we're not stepping into this strange, this different territory. We are doing the same things, but this is more of a general linear model approach. And I'll talk a little bit more about that when we get into modeling non-interval or ratio outcomes. A little bit more on that. So just as kind of, so here's the slope from our home environment score on this behavioral problem index. The question for maximum likelihood is, how do we arrive at this slope? And this will be important for essentially how we're stepping into multi-model inference as I get to that. So first, for any given regression model, we have a likelihood function, which governs the probability of the data. It governs the likelihood that certain parameter values would be able to produce the data. So essentially, when we think about a likelihood function, we're thinking about the choice of what's the distribution which governs the likelihood of observing particular data values, and as such, particular residual values. So most often, like when we're looking at, so OLS regression, many linear models is we're working with a Gaussian likelihood or a normal distribution. So let's say that if we assume a normal distribution, for the error term, what we essentially get is a particular probability of observing certain errors of a certain amount. So errors that are really large, errors that are really small, errors that are really close to the mean. What's the shape of it? So if it's normal, you would assume that the shape of that error structure would be normal. And what the model is essentially trying to do is estimate the likelihood that, and so literally this value here, the likelihood is the probability of simultaneously observing all of the data points as they are. Now, conceptually, this might be a little difficult to step into, but recall that. So with maximum likelihood, what we're trying to do is, given the model, what are the parameter values that maximize the probability of the data? So it needs to quantify that in a way. So what we essentially have is the likelihood of simultaneously observing all of the data points as they are. Now, as you might think, now that likelihood can range from 0 to 1. And if we had a likelihood of 1, that means that our model perfectly could reproduce all of the data points. As you could imagine, no model is going to get that high. And in fact, most of the time, our likelihood value is going to be ludicrously small in terms of 0.00000000, just going on and on and on. Because just think about that. The probability, parameters that could produce the probability of observing the data exactly as they are, that unit 1 would have this Y value, this XIT value, this W value. Unit 2 would have this Y value, this XIT, this, so and those things, could be related to each other as well. Oh my goodness, there's no way that value is going to be big, all right? So because that value is often very unwieldy and difficult to estimate, usually what we will do is a model will try to maximize the log likelihood. So take the log of that, the logarithm of that value would be some number that is, it usually will be, infinitely negative going up to 0, but its variance will be relatively stabilized. And so listen, this kind of stuff isn't all that important for you to recall. I mean, it's here. I don't know if I could work with this myself, but essentially the likelihood is extremely small, has a ton of zeros. We take the logarithm because it's easier for models to arrive at that value. So then what we'll do is, once we have the log likelihood, is if we take the log likelihood and we multiply it by -2, this will produce a value called the deviance, or you might see it in some software called the -2 log likelihood. And the reason that we do that is it will produce a value where essentially it's a minimization criteria. If it has a value of 0, then that means the model has a perfect fit, and larger values indicate worse fit. So any kind of maximum likelihood estimation is really trying to minimize the deviance function, which is what makes it, it's trying to be conceptually similar to the sum of squared residuals. So an OLS model will be one of the parameters that minimize the sum of squares. Maximum likelihood is saying, okay, well, give me a value that maximizes the log likelihood, or equivalently minimizes the -2 log likelihood, or the deviance function. Okay, so what we are doing is when we perform maximum likelihood estimation, it is searching for parameter values that will minimize the value of that deviance function. And when it does that, we get that given the model and the way that we've specified it, these are the parameters that maximize the probability of the data. Now, in order for it to arrive at these, it will run through what are called iterations. So essentially, it will start with a set of like candidate values, and then it will search for potential parameter values using very informatively named technique called, I think it's called like the numeric method, or something like that. Sometimes it can fail. And so that's when you might estimate a model that will say that it failed to converge on a solution. That means that it searched, and it searched for as many times as you told it to. I think the default in R might be 100 iterations. You could set it to 100,000, or something higher. It searched and searched and searched, and it could not find a set of parameters, like essentially the values when it would move around searching for new parameters, the deviance would not move in a way that the model expected. It could not arrive at a unique solution. That can happen. We'll cover some of that later. So one of the reasons I use Bayesian methods in my research is that we can kind of sidestep that problem a little bit by using a smarter searching method. But essentially, it will try to reach a set of parameters that are close enough to what minimizes the deviance function. So sometimes the error variance that comes from maximum likelihood is a bit of an underestimate of the population variance. So what you might hear attached to maximum likelihood is something called restricted maximum likelihood, or REML. And what REML does is it provides a bias correction dependent on the number of parameters that are in the model. So restricted maximum likelihood models, if they are very, very large, they will, or if they have a relatively small number of parameters, the REML will be different, from the actually, no, I think it's a large number of parameters. They'll be different from the maximum likelihood estimates, but the larger the sample size, gets. So larger sample means you can estimate more unique parameters. The REML and the just regular ML will have more similarity to one another. So this will have some implications for how we do model comparison, but we'll talk about that later when we get to that. So, essentially now we've kind of set out, all right, so we have panel data, we want to perform a regression analysis. We have talked about the way that parameters are being arrived at, using maximum likelihood estimation. This is just some background, for us to work with. We see that we can model a dependent time structure, by adding a categorical variable for time. Let's start getting more systematic about how we deal with this. So now what we want to do is we understand that there's within unit variance, there's between unit variance. We thought about the dependency of observation, that is like how different observations from the same units are related to one another, as being a problem of unobserved heterogeneity. So that is, there's something about units that make their repeated observations similar to one another. So what do we do about that? So in class today, we will talk about two approaches. So robust standard errors, or a way of saying, regardless of the nature of that dependence, depending on how much dependence there is, let's penalize our standard errors based on that so that our results, our parameters, and our conclusions about statistical significance will still be correct, even if there's any kind of dependent structure. And then generalized least squares, which says, let's think about what that dependent structure looks like and try to incorporate that information into our model. And it turns out we could actually use both of these at the same time, but let's talk about them in kind of order here. So first, robust standard errors are kind of the Advil of dealing with unobserved heterogeneity. So here's the model that was estimated before. So this is with maximum likelihood. So you can see I've estimated with the GLM function in R with a Gaussian likelihood and identity link function. All right, so that is an OLS regression. So here we get our estimates. Recall that So, we have essentially our time varying variables, how they're related to the outcome. Is the data, consistent with the parameter being 0, yes or no, et cetera. So first of all, in this model, there's no correction for the dependent structure. We have corrected for baseline changes in Y over time that affect everybody equally with these categorical variables, but we have not provided any kind of correction for this, the dependent structure in which how are the values of the behavioral problem index at time 1, or as it was measured in 1988, how correlated are those with time 2, with time 3, with time 4? What about the measure of time 2? How is that correlated with time 3, with time 4, time 5, et cetera? We've provided no correction for this. OLS regression, or just maximum likelihood with no correction for dependence, assumes that all of these will be equal to 0. Okay, so OLS assumes all this is equal to 0. I mean, I'm looking at it. It certainly doesn't look like 0 to me. So under robust standard errors, what we could do is we could take a look at the variance covariance matrix, between our parameters, especially for these dependent observations, and we could correct them, essentially penalize them based on how much dependency there is. So how much of that correlation is there? And, so like previously you might have seen this done just based on heteroscedasticity. This can also be adjusted for clustering of observations so that you have observations coming from the same units. So here, this is conventionally in matrix algebra, the variance covariance matrix, where we have the residual variance over the different parameters, the predictor values here. Under a robust one, just notice here, so we have that matrix up here, okay? But in the middle, we also have this new matrix that's being estimated. And this is called, these are often called sandwich estimators, or Huber-White estimates, lots of different variations on these, but essentially these are referred to as sandwich because in the middle we would have 2 bread matrices, and in the middle we would have a meat matrix that can take on different forms in terms of how it's attempting to handle residual variance. One thing I just want to highlight here is that we have both. I borrowed this notation from somewhere else, but we have I and J. So you can think of J as being our T subscripts. We are incorporating information about residual variance, both between units and within units here. All right, so we are getting a correction for dependence based on the fact that there is dependency here. So in R, this can be estimated with the club sandwich package. So club sandwich has a coef test function where essentially we feed it the original model. We ask what is the robust variance covariance matrix we want to use. Now there are a lot of these. Now Stata is very well known for how easy it is to estimate different robust variance covariance matrices by using comma VCE robust, for instance, you might be familiar with. So here the CR1S matrix is the default that Stata uses for its cluster variance. This is provided here for an alternative. I see no reason not to use that in this case, but if you really want to get to the econometrics literature, you could find some of that information. So again, usually when I refer back to something with Stata, I'm referring back to a workflow that is related to economics, because Stata is very much an econometrics tool. So we indicate which type of matrix we want. We indicate the information on the clustering. So what's the variable that identifies the unique units in our data? So for us, it is the ID variable. And then how do you want it to compute the test statistics? There are a few different alternatives here. There's no reason in this case not to use the naive t, which is basically give us our parameter estimate divided by our robust standard error. And that will give us, we have a corrected standard error, so we have a robust t statistic and now a new p-value that comes with that. Okay, so based on this, you could go back to the previous output and see some of the differences. The main thing to highlight here is, so the parameter estimates will all be the same because we have not corrected those at all. They still include an ambiguous mix of information from between unit variation and within unit variation. But what we've done is we've corrected our standard errors for dependency. So we've corrected them for the fact that we have repeated observations coming from the same units, and if there's heteroscedasticity, we have corrected for that as well, which is nice. One of the nice things about using these types of robust estimates. And so one thing you might notice is that this standard error is considerably larger here than in the previous model. This p-value, we're still rejecting the null hypothesis here, but it is a little bit more in line with the potential that we could obtain data like this, assuming that parameter is actually equal to 0. Yep. Yeah. And so this here is looking at the standard errors for each model, and then looking at the ratio of the standard errors from the conventional estimation to the robust estimation. And so you can notice that some of these are larger corrections than others. The variance for time is less than is actually in the other model. I can't remember exactly why that happens. This might be just due to the features of these particular data. I don't know if we could expect that all the time. But the thing to note is that the amount of correction will vary from variable to variable. And so there are some, depending on the amount of dependence, that you will get larger corrections for. Often those variables that do not vary over time, are the ones that we get the most incorrect variance estimates for, because the model sees that, if you have no correction for dependence, it sees that the values of, oh, wow, this person was male every single wave of these data, there's not a lot of variance in this, so the standard error will get smaller. It now recognizes that these are coming from the same individual, and so it's providing a larger correction for that. Now, yeah, okay. So usually, when you have a correction, for the robust cluster variance, it will be larger than the conventional variance. But if there's little dependence, between your observations from time point to time point, then there's actually little to correct. And so in those cases, you might not expect the robust variance to really be any different, from the conventional. This does, and because they also correct for heteroscedasticity, this does lead to some circumstances in which researchers might feel pressured to do a robust variance estimate, even if the model, it's not really necessary to do it, just because this is kind of the way it does draw a bit of a line between how econometricians like to think about these types of problems and how other, especially Bayesians, think about these types of problems, where there's a great example. It was a back and forth between, well, it wasn't really back and forth. It was somebody says something and somebody responds. But John Wooldridge, a very well-known econometrician, Michigan State University, my alma mater, said, I am intrigued by, Bayesian inference, but I don't find it to be as robust, as econometrics tools, because let's say that I want to estimate a model that can accommodate any likelihood function. that could accommodate any variant structure, and I will still get correct, correct parameter estimates. It's robust in the sense that even if we try to specify something and we're wrong, we will still get a at least a mostly correct solution, even if we are penalizing our variance estimates by quite a bit. And Andrew Gelman, a well-known Bayesian statistician, was asked to respond. And he said, well, I mean, that makes sense. And John Wooldridge doing econometrics work is probably better than John Wooldridge doing Bayesian work. But when you think about it, do you really need a model where any, residual structure can be accounted for, where any likelihood can be accounted for? I mean, isn't it more likely that there are certain likelihoods that are going to, be the best fit for this model? And that's the kind of decision making that's kind of counter to this robustness. So like thinking more about, okay, well, how do we model and capture that information, as opposed to like, I don't really want to have to think about it. If there is dependence, I want it corrected. That's what robust standard errors will do. Again, the amount of correction is not particularly strong, just using these on their own. So that's why I think of this as kind of the Advil, approach. But it does lead some people to, because of that, just, just set it and forget it, kind of approach. I think it does lead some people to apply them when they might not necessarily need to. So again, if you're seeing that you do have dependence, but there's very little correction, sometimes it's hard to justify not doing them. But if it's changing conclusions, I mean, that's one thing to keep in mind. Just note that usually with these types of robust estimates, if you have just like 20 units that are observed, multiple times, that's a pretty good minimum point where you can start using these types of robustness checks, robust variances. I mean, but your data need to be balanced, meaning you have no missing observations across those time points. Once you get to unbalanced data, which most of our data will be, that's when you need larger ones in order for those variance estimates to be correct. Okay, so that's robust standard errors. That's something we can apply to just about every one of these models here. Yeah, actually we can to every one of these. We could apply basically robust variance estimates that account for dependence in some way. But again, that robustness approach is just, if there is dependence, I want it corrected. We'll now talk about generalized least squares, where we try to think a little bit more about what that dependence looks like, and if we can take some of that information with us into our estimates. So I think this is really intriguing. I kind of like this stuff, so hopefully you will too. So let's say we have panel data. We want to conduct a regression analysis. We recognize that just a standard maximum likelihood, Gaussian likelihood for identity link, assumes there's no correlation between the residuals here. That's not going to happen when we have panel data. There should be some correlation between the residuals. We could expect that because the observations are coming from the same units. So if that's the case, we still want to use regression. This is where general least squares can step in. So what it will do is it will provide correct parameter estimates and standard errors by taking some sort of correlation structure into account to both the parameters and the variance estimates. What we need to do as the researcher who is specifying the model is we need to specify the appropriate structure for the correlations. So let's see what that looks like. So first, just kind of understanding what we're doing here. In matrix algebra terms, this is how we would arrive at conventional OLS or Gaussian maximum likelihood estimates. Again, like when I used to teach my regression class, I would do a lot more matrix algebra. I don't do a ton of that here. It's a bit of a distraction, but the thing that I want you to focus on here is the difference between these two equations is that there is this new matrix here called omega hat which appears on both sides of this, in between the different terms. Now, what omega hat is that it's a block diagonal matrix for the error term. It's a matrix that describes how the residuals from one observation to the next are correlated with one another. Now, these matrices can take on a number of different forms. So, for instance, this is a really simple example just to show you with, we have, so basically 3 individuals who are each observed 2 times. What we have are these different rows, these different, as in the Greek letter rho, RHO, these different correlations for different time points. So we have essentially, 1, 1, so we have an estimate for the variance of residuals at time 1, 2, 2, an estimate for the residuals at time 2, and on the diagonal for each individual, we have how are the what is the correlation between the residuals at time 1 and time 2. So we're now, now again, OLS would assume that this is 0 across the board, all zeros in this matrix, and that thus we wouldn't need to include it up here. But now what we're doing is we're actually allowing those correlations to be estimated in some fashion. Now, what fashion is that? That's our task with GLS. So in R, these can be estimated using the NLME package, which is one of the multi-level modeling packages in R. It's just in this case, we aren't specifying random effects for parameters yet. So again, we will do that soon. But we have our formula, and we're including our categorical variable for time. So we're still taking that information about time, things that affect all units equally from time point to time point. We are essentially dummying that information out. And what we're doing now is we are specifying essentially a structure, for the correlations based on the individuals and based on the time points. Now, this one that we're doing right here, the core symmetric, is this is going to estimate what's called an unstructured variance covariance matrix for omega hat. Now, what an unstructured matrix does is that there's literally no structure to the matrix. Every pair of time points are given a uniquely estimated correlation. So what do I mean by this? So right here, so we estimate this model, we get our output. Here, we now have a correlation matrix. Now think of this right here as, let me just go back a few slides. Oh my goodness, how far back do I have to go? Think of this as this. It's an estimate of these different correlations, okay? So these are all new parameters that are estimated with the model. A parameter reflecting correlation of time 1 and time 2, time 1 and time 3, time 1 and time 4, time 1 and time 5, time 2 and time 3, time 2 and time 4, time 2 and time 5, etc. They're all given a uniquely estimated correlation. Now, we are chewing through a lot of degrees of freedom to do that. So just think about, if we want to estimate a model, that is parsimonious, we are eating up, a lot of parameters by allowing every single pair of time points to have their own estimated correlation. Now, just note, still, OLS assumes that all of those are equal to 0. It's clearly not correct. In addition, we also get information about variance multipliers from GLS. This is just information that comes from, it's reflecting on heteroscedasticity. So again, this is our residual standard error. It's indicating how much the residual variance at different time points changes. OLS assumes that these are all equivalent to 1. These aren't that bad. Heteroscedasticity doesn't really seem to be that much of an issue for this model. But what we could do is, if this was problematic, we could estimate this GLS model with robust standard errors as well. So we could do that too. So these are the parameter estimates that we get from this. If we summarize it, what this has done is we have parameters and errors and test statistics in which the dependent structure of the data, which we have specified as unstructured as every pair of time points are allowed to have their own residual correlation. That information has now been taken out, and these now have that correction for dependence. So correction for unstructured dependence. If we compare across, we can actually see that there's some similarities and some differences. So for instance, for our poverty, effect, this really has not changed that much. But I mean, look at the size of our home environment effect. That has changed quite a bit. It's decreased by about 60%. I think that's right. And so we're still arriving at the same conclusion. We're still seeing that the more positive a home environment is, the lower behavioral problem and the behavioral problem score will be. But after doing this correction, that amount of change is quite a bit smaller than we had seen before. So it seems like part of this conclusion is being driven, by the fact that observations are coming from the same people. So their home environments perhaps are not really changing that much over time, is one thing we could conclude from this. So if we want to determine, okay, so is this better? Now, again, we are going to get into multi-model inference, later in this class here, but we could at least start off with essentially the equivalent of an F-test, for maximum likelihood, or a likelihood ratio test. This is looking at essentially the deviance function. So even though this says log likelihood, it's really the deviance, but it's the deviance function for the first model, the uncorrected model, over the unstructured GLS. So note, oh my goodness, look at the change in the degrees of freedom here. Like, whew, we have expended a lot more parameter estimates here because we've allowed every single pair of time points to have their own correlation. Even though we've spent all those additional parameters, this indicates that it has been worth it, that we have improved the fit of our data in terms of comparing the deviance functions for each of these. Okay. So unstructured matrices, if you have a small number of time points, like 5 or fewer, an unstructured matrix will usually be the best fit. The reason for that is that the amount of parameters that you're expending, to get your correction is not tremendous. But imagine, but you are essentially like, what could be a better fit than allowing every single set of time points to have their own correlation, right? It's tough for a more parsimonious model to get a better prediction than that. However, if you have more time points than that, so let's say I've got 50 US states or 3,000 US counties, and I have them at 20 different measurement points. Think about how large that unstructured matrix would be. Every single pair of time points would have a uniquely estimated correlation. Holy smokes. I mean, that's pretty, that's very computationally intensive. I mean, look, your computer will still do it, but you are expending a ton of degrees of freedom to get that information. And when you're doing that, it's going to rely on that huge sample size. So if you're in the situation of the 3,000 US counties, 20 time points each, you could probably pull it off. But 50 US states, you're now looking at your unstructured correlation matrix is now the residual correlation matrix now has more estimated parameters than you have actual unique unique units. That's bad. That's not good. So here's a great depiction of an unstructured covariance matrix in action. Thinking about, oh man, so here's the correlation between time point 1 and time point 2, and then here's the correlation between time point 2 and time point 8, and then here's the correlation between time point 8 and time point 20. So it is estimating all these separate time points. And what we need to ask ourselves, is, do we really need that many? Do we really need to say, like, no matter how many time points there are, you get a parameter, and you get a parameter, and you get a parameter, Oprah style? Or can we be more parsimonious? Is it really necessary that when you look at that correlation matrix, of your residuals, is it really the case that every one of them needs a separate parameter? So there are a few alternatives that we could do here. So these are their names under different fields and in the NLME package, but they're often called, have different names here that you'll see them referred to these as different fields. So first, there's an exchangeable structure, or the compound symmetry, as this is called. Now, what an exchangeable structure does is it estimates one correlation to say, all right, you have observations that are coming from different time points, coming from the same individuals over time. What if there was one correlation that could reflect how repeated observations are related to one another? Now, that might sound quite simple, but when you think about that correlation matrix that we saw before, again, you have to go back 100 slides to see it now, but like those correlations really aren't that different from one another. So you could think about an exchangeable structure as, as like a regression line, drawing the best fitting line between a set of correlation points. That might be enough, if it's unbiased. Now, this type of exchangeable structure is actually the default variance structure for most multi-level models. When you estimate a model with LMER, in R with mixed, or TX or XT or whatever it is you call it in Stata, or proc mixed in SAS, usually the exchangeable structure is what is assumed, that there is one correlation that can account for everybody. So a lot of times this is not actually even thought about here in estimating these types of models, that it's just assumed that we can capture residual dependence with a single value. That just, there is dependence, here's a value that reflects that. And another way of thinking about that particular one is that, observations are correlated with each other because they come from the same unit, right? So because they're coming from the same unit, there is some degree of dependence you should expect, and this is the degree of dependence regardless of which unit we're looking at. So an alternative is an autoregressive structure, or an AR structure. Now, what an autoregressive structure does is it says observations that occur adjacent to one another are more similar to each other than observations that are farther apart. So it assumes that there is a decay in correlation over time. Now, you think about, okay, like if we're taking measurements, of our units, so from time 1 all the way up to time 5, like you are at time 2, you are more similar, to how you were at time 1 than you are at time 5. Time 5, you are probably still some similarity with time 1, but it is assumed to be less than time 4, 3, or 2. Right, so it decays. Now, an autoregressive structure of 1 is the kind of default here, where it assumes that there is essentially like one, like who you are at time 2 is based on who you were at time 1. An autoregressive 2 would be like who you are at time 3 is related to who you were at time 2 and who you were at time 1, or what your scores were at those two things. And those correlations are allowed to be different, but there's always decay. So you think of it as like waves of decay. So autoregressive is used, has a lot of different uses. You could think about a lot of different phenomenon as following autoregressive structures. So like gravity is known to have a well-known autoregressive structure to its strength, in which, the strength of Earth's gravitational pull, is strongest when you're closer. And as you get away from Earth, that decay is not a straight line. It decays like this. That is an autoregressive structure. So a Toeplitz structure, or an ARMA structure, is a correlation among your residuals that's based on, and I'm going to go through estimating each of these different models, and we'll talk about these just so you get a picture of it here. So a toplet structure is every pair of time points is allowed to have a correlation structure. Now, not so like there's a distance between two waves. So like if you go from wave 1 to wave 2, there's a correlation of residuals there. Now that difference, that's a one wave difference. So that's the same as if you go from wave 4 to wave 5 or wave 2 to wave 3. Now there's a two distance one. So anytime you go from wave 1 to wave 3, there's a correlation. So that's the same as a 1 to 3 is the same as 2 to 4 is the same as 3 to 5. So you can specify how many of these do you want to do. So here a distance of one wave is a specific correlation, 2 is a specific correlation. If you, let's say we have 5 time points here, so there are 4 sets of distances. 1 to 2, 1 to 3, 1 to 4, 1 to 5. Yeah, so 4. Usually you want to specify, t minus 1, for that. But so we would say p equals 4, for 4 separate distances. If we only said t equals 2, then it would assume that anything that is greater than a 2-wave difference would have a correlation of 0. Probably not a great assumption. So usually you do t minus 1 for this. And then there's an exponential. I don't have a lot of experience with this one personally. This is used when your time is a continuous variable. I haven't seen this very often. I'm going to skip this for right now. Maybe in your field it's more relevant, but we're going to talk about these 3 a little bit more. So first, here's our exchangeable structure or our compound symmetry. So here in this case, what we get is we get a single correlation that essentially reflects the fact that, okay, responses are coming from the same units over time. For any given unit, what is a value that we could use to capture the degree to which those responses are correlated? So we get one value, this rho value here. And you notice that if we then say, okay, well, give me the variance covariance matrix that this exchangeable model uses. And you see here are the correlations between those residuals. They're all the same, all right? Because it assumes there's one value that is being used to capture that information. Now, again, think of this as an approximation. Think of this as we estimated, we had this residual structure. How can we capture that information? Is this a good way to capture that information? Like, again, those correlations aren't terribly different from one another in the actual observed data. So is this really that bad? Again, we will use multi-model inference to figure that out. But in this case, there's one correlation. Now, incidentally, under multi-level models, when you estimate one and you have your separately estimated intercepts or different slopes for each parameter, they're in the data. When we assume an exchangeable structure here, the intraclass correlation or the amount of variance that is in the outcome that in the residual, that's between units, is this value. Like this is basically an ICC here. But again, more on that later. Okay, so here we have our autoregressive order 1. This is a good point for me to stop and ask here. When you look at this, can you identify? So like notice this decay that's happening here. How would you arrive at this decay? What's the relation of this value to this value to this value to this value? Just think about that for a minute while I take a sip of coffee. Maybe pause it. Right. So as you think about it, if you take what is the square root of 0.60, all right? So, what's squared? So 6.60 times 0.60, you will get this value. What is 0.365 times 0.365? Get this value. No, wait, it's Well, here I am looking like an idiot. Let's figure this out. There is something here. Shoot. Oh, that's right. Times point. Yeah. So basically, 604, 0.604 squared, 0.604, cubed, 0.604 quartered. I don't know, but basically keep multiplying it by this value and you will get this decay function. All right, so that's the autoregressive decay. Now, if we were to do an AR2, we would get another set of correlations that would reflect how time point 1 was related to 2 time points later. But AR1 is usually a good starting point where we're essentially saying how you are at one time point is dependent on how you were at the previous time point. And the closer you are to a previous time point, the more correlated your values will be. That's usually pretty sufficient. Okay. So this is a Toeplitz structure. This is a Toeplitz 4 or T-1 because we have 5 time points. So right here, these are our correlations for the different distances. So this is how 2 waves, or at least 1 wave apart are related, how 2 waves apart are related, 3 waves apart, 4 waves apart. Again, it's weird that this switches to negative and being quite small, but you would expect that the more waves you go, the less correlated your values would get. So right here, these are those estimated correlations. So notice, like we could go down this matrix. This is our, we have 1 wave, 1 wave, 1 wave, 1 wave, 2 waves, 2 waves, 2 waves, 3 waves, 3 waves, 3 waves. And so these are the, the different variances, here for those. So again, if we were to go Toeplitz 3, or something like that, it would assume that that left out distance is 0. And in some cases that might be fine. I think it's usually safe when you have a small number of t, like we do here, that you could go for T-1. Okay, so how do we choose which one of these is the best fitting correlation matrix for our residuals? Now, so there's a few ways to do this. I'm a big fan of using information criteria. Or in this case, we have the AIC, we have the BIC. So Akaike's information criteria is basically the deviance function plus 2 times the number of estimated parameters in the model. So what the AIC does is it gives you a number that is penalized by model complexity. So again, 2K. The more parameters you provide in the model, the bigger and bigger that correction will get. The smallest, the smaller the AIC, the better the fit. The Bayesian information criteria, there's really nothing Bayesian about it. But what the BIC does is it provides a stiffer penalty for model complexity, where instead of just 2K, it's K times the logarithm of the sample size. And what this does is it really provides a stronger correction to say, depending on how complex the model is, so how many parameters you estimate, and the size of the sample that you have to estimate those parameters, that's the penalty that it will provide to your information criteria. Now, again, the smaller the BIC, the better the fit. But relative to the AIC, the amount of correction is much larger. So the BIC really says, so look, if you're estimating all of these different parameters, they really need to bring something good to this party if they want to get in the door. Like when you estimate different parameters, they need to be providing some predictive accuracy. And that's really what these criteria are doing. Because when you think about, okay, so the deviance function, we're minimizing that log likelihood, which is the probability, of the data all simultaneously being observed as it is. So what it really is it's a measure of how well can your model predict the data. Now, whether that is viewed within the sample or out of sample, is something that a little bit more of an advanced topic, but again, it's a measure of predictive accuracy. The AIC and the BIC, I usually prefer the BIC because I prefer to take more conservative approaches quantitatively. But depending on your field, there might be a preference, for one or the other. And then we could also do a likelihood ratio test of different models, compared to one another. This is a much more liberal compared to the AIC and the BIC. It's much easier to reject a null hypothesis with the LRT. So I'll advocate you do one of these two. So here, what you would want to do is specify each of your models and compute the test statistics for them. So in R, this could be done using the ANOVA function. So not to be confused with I'm comparing means across 3 groups. So like that ANOVA, the analysis of variance, this is a model comparison function. We can give it our models and it will compute AICs or BICs. There are also dedicated AIC and BIC functions. In Stata and SAS, it might be necessary for you to simply estimate each model and write down those individual AICs and BICs as they come out. But here, okay, so we get a set of AICs and the BICs, and notice that the BIC is universally larger than the AIC because of the amount of penalty correction, the BIC does. And then we have our likelihood ratio test where we could compare one given model to another. So is a Toeplitz better than an exchangeable, for instance. So how do we evaluate this information? So this is a pretty good criteria here. So basically, for any information criteria, the smaller the value, even if it is small by a very small amount, that indicates better fit. Now, we can use this for indicating how much of a better fit there is. So when we compare the BIC, from one model to another, a difference of just 2 points, and this does not depend on the sample size. So if you have models with millions of observations and you're comparing the BIC from one to the other, you're still using this amount, for is one model a better fit than the other. So a BIC of just 0 to 2 is a weak indication of a better fit. A difference greater than 10 is an indication of strong fit. So you can still use 0 to 2 as, yes, I'm selecting the best fitting model, but it's a negligible, amount of improvement. So down here, we would have a pretty strong amount of change from 10. So we can go up here and take a look. What are our deltas here? So we can see that the smallest BIC is a Toeplitz 4. And so recall again, just think, what are we doing with a Toeplitz variance, residual variance correlation? We are allowing separate correlations for distances. So a distance of 1, a distance of 2, of 3, of 4. So when we look at the next best fitting one, exchangeable is actually the best fitting. And so when we see the difference here, that's a difference of about 29, 31, one of those two, of about 30. That's a strong indication that a Toeplitz 4 is the best fit here. We actually see that the worst was provided by the autoregressive, and part of that might be that autoregressive would fit better if there was a much more defined decay structure to our correlations. There's a little bit of decay, but an AR1 was not capable of capturing the nature of that decay very well. So it has the poorest fit. And also note here too, this fits even better, by 36 BIC. It fits even better than an unstructured matrix, which had a separate correlation for every single pair of time points. So this is like saying, yeah, you could do that if you wanted, but you really don't need all of those parameters to capture that amount of variation. So we were able to get a better fit with just 17 estimated parameters compared to 27. So another way that we could encapsulate this information with this type of model comparison is with a statistic that's called the weight of the evidence. So this is something that's covered in the long chapter for the reading here. So this is a value that will range from 0 to 1 it will sum up to 1 for all the models, essentially saying, so given the data and an unknowable true model that we, hopefully have estimated here, what's the probability that a particular model is the best model to approximate the true model? And so this will, kind of take that sum to 1 value and divvy it up among your different models, and then say, so which of these is the best approximation of the true data generating process? Usually you want a weight that is greater than 0.9 to indicate a best fitting model. And in our case, we can obtain this information from the package AIC mod AVG, a weird name, but it has a function called BIC tab. And so we can give it our models. I also opted to give our models names. You could just kind of see what structures we have here. So it will order them by the weight of the evidence, and the Toeplitz wins hands down here in terms of the best fit to the data. So in this case, we would conclude, if we want to be somewhat more principled when it came to, all right, rather than just like, we understand there's dependence, I want estimates that will reflect, these associations regardless of the nature of that dependence. We can say, well, let's think about the shape of the dependent structure. What's the best way that we can capture that information and then get corrected beta parameters and W parameters, or gamma parameters for W variables after that information has been corrected. So here we see that Toeplitz is the best fit for that. Now, what I want you to think about here is when we do multi-model inference, I really love this analogy. I got this from Stephen Vasey in a workshop I did with him, is that we can always think about multi-model inference as being this comparison of different worlds. So again, I use multi-model inference for everything from testing interactions to selecting different variance covariance structures, but it's like, we are trying to imagine the world that produced our observed outcome, our observed data, where it's like in one world, basically there is no correlation, between how you are at one time point to another time point. In another world, there are correlations, and really like every single, how you are from one time point to another is allowed to have its own wildly estimated correlation. That would be an unstructured one. How you are from one time point to 2 time points later, or how you are from 1 time point to 3 time points later, those have their own correlation structures. That would be a Toeplitz one. And so here, like, which of these worlds is the most likely one that produced the data that we have? That's what this type of multi-model inference is doing. So what we can see here is, like, in this particular paper, what they did was, what you would want to do is, okay, an empirical approach for specifying which correlation structure you do. So we have our model. You run all of these different correlation structures before you ever get down to presenting results or interpreting results, looking at your p-values, any of that stuff. You can specify, you would test which of these produce the best model fit, and then move forward with that. And you present this information to readers. So like under this particular one, we could see that the best fitting model, I'll go over here to the BIC, is actually a tie between an exchangeable and a heterogeneous autoregressive. So I'm not sure what that is. Again, maybe that's an AR2 or something like that. But these are more or less negligible differences, from one another. But here, even the AIC indicated that the Oh no, just the autoregressive. Oh, good. I know what that one is. Yeah, so it's either exchangeable or autoregressive for the choice here. In those cases, if there's really like a tie between the two, you might want to estimate both and see, just look at the parameter estimates and really see if they're different. And if they are the same, then you can think about the nature of that correlation structure and whether or not that really makes sense, for the data as you think about them. Just be transparent, for readers. I think the last thing that you would want to do is just assume one of these from the outset and just estimate that model and not talk empirically about how you arrived at this, or theoretically how you arrived at this as being the appropriate variance covariance structure. Okay, so so next week we are going to start getting into multi-level models and fixed effect models as, okay, so like we have thought about the dependence as being these different variance covariance structures. Perhaps we can take an additional approach on top of those things, because we could add those on. We could always do a multi-level model, or a fixed effects model that had some, different variance covariance matrix to them. Maybe we should start thinking about how we could really be more systematic about parceling out that within unit variance from the between unit variance. And so that's what we'll get into next time. But I will highlight here, because I said that this is something that we would do, is when we think about the analysis project. So again, the example data set that I have here, which you are more than welcome to use, but it sounds like a lot of students have data sets that they are interested in themselves and are interested in working with. In this particular example, kind of what we've done is you have enough information now to get close to doing these first two. So I have this as a little bit different of a setup, but in the first set is that you would estimate just that maximum likelihood model, the OLS model, treat time as a categorical variable, and interpret those results, look at the correlation structure, and explain why a model that doesn't correct for the correlation structure might not be optimal. And then here, I do have in these particular results, I think this might be because of the way that Stata handles GLS, I'm not sure, is that what you could do is then step into the GLS, okay, well, let's do a generalized least squares model and specify how different correlation structures, might be a good fit to these data. So you could get to a point now where you're taking that initial model and you are testing different correlation structure. So in this one, I think I had just asked for these specific ones. You could test additional ones based on the number of waves that you have, or if you wanted to do, an exchangeable one, just in GLS outside multi-level model. In this one, I can't remember exactly why I set this up, but it's always possible when you estimate a multi-level model to then also screw around with the correlation structure. And it's the same for any Bayesian multi-level model as well. So again, you can start kind of playing around with this with your data and looking at what I would hope that you would maybe check out in this case is at least let me look at these correlations, let me estimate different models and use the AIC or the BIC to compare those, and can you make a determination about what the nature of that correlation structure is? So, I know that R can handle the different correlation structures with GLS. I know that SAS can. I am not sure about SPSS or Stata. That might be why I specified it in this way. But again, it's just goal should be, can we specify different correlation structures and compare across models? Okay. So anyways, that's it. So thanks so much. Please, if you have any thoughts or musings about this information, the type of stuff that we covered here, please put those into the discussion board. And I'm looking forward to being back in class next week. And I'll talk to you then.